Now that we've discussed free fall, the motion of objects moving through the air in one dimension, we're going to actually start to expand that discussion into looking at projectiles in two dimensions as well. Specifically, though, we're going to focus only today on horizontal projectiles. So what is a projectile exactly? Well, it's any object that moves under the influence of gravity, but no other forces. So only gravity, don't want to care about anything else. So let's bring up a few examples which are commonly thought to be projectiles, and let's see which ones are and which ones are not. Well, if I have something like a baseball would be considered a projectile, any sort of ball, cannonball, bowling ball, basketball, anything like that, because as soon as it leaves your hand or leaves the cannon or anything of that nature, the only thing acting on it is gravity. So baseball, any sort of ball, that's A-okay. Well, what about a plane? Well, a plane has a couple of different issues here. First, a plane is self-propelling because it has engines. So that is already going to be a force acting on it additionally, but also it has wings, and those wings get lift from the air around them. Now, we are ignoring air resistance, but even if we do that, it still has the engines, so this would not count as a projectile. Same thing with a rocket, also self-propelling. We say it has the force of thrust from the rocket engines, so this would not count either. Well, what about a bird? Well, bird doesn't have any sort of engines or anything like that, but it does have that lift from its wings. So we're going to go ahead and say that is not a projectile. And lastly, what about a bullet or something like that? Bullet, a dart, something of that nature. Well, all of those, once they leave the gun, would once again be a projectile because the only thing acting on it would be the force due to gravity. So we will actually notice that what we discussed so far in free fall, so objects being dropped and being tossed straight up and down, those are actually both examples of projectile motion. However, they are projectile motion in only one dimension. We're now going to focus on projectile motion in two dimensions. Now, to start this two-dimensional projectile motion, we're going to focus exclusively on what we call horizontal projectiles. And what that means is that it's a projectile that is launched horizontally, but that means its initial velocity, so at the instant it is launched, it is only in the horizontal dimension. So if we look over here at this cannon that's sitting on the edge of a cliff, this cannonball is launched. We're going to say this is the instant after it has left the barrel of the cannon, its velocity is entirely horizontal. But I think we can all agree that we know that this projectile is not going to stay entirely horizontal the entire time, which would make a whole lot of sense, because what is the shape of its trajectory actually going to be? Now, quick note real fast. This word, trajectory, may be new to you. A trajectory just means the path of the projectile. It's just the path that the projectile goes through. So what is the shape of this trajectory? Well, I think we can all agree it's going to be some sort of curve. Now, that curve actually does have a specific shape. It's actually a parabola. We might see in a minute why that is, but it is a curve, not obviously a straight line. Now, before we start analyzing specifics, we need to really examine something a little more closely. Let's imagine we have two projectiles, the one on the left over here, and the one on the right. And let's say the one on the left is dropped, and the one on the right is, we say, launched horizontally, just like we discussed, from the same height. And the question is, which will hit the ground first if they start from the same height? So the one that is dropped or the one that is launched horizontally. Now, we should look at something about this in class, so this should not be entirely new to you, but take a second and think about it, because the result might be a little surprising. Most people, well, really, I've seen both answers said here. I've seen that some people say, well, the dropped one's going to hit first because it has the shortest path. And some people have said, well, the launched one is going to hit the ground faster because it has more momentum or more force or whatever we want to say. It has more oomph when it leaves the cannon. But actually, the right answer is that they land at the same time. Now, granted, this is ignoring air resistance, but we're ignoring air resistance in this entire unit, so that's nothing new. So if I drop one and launch one, they will go and hit simultaneously. But why does this occur? Why do they hit the ground simultaneously? So let's go through this a little bit more step by step. First, let's just kind of scale out what the paths will look like. So let's say after some set interval of time, this can probably be a fraction of a second, t1, they are at these positions. At the next interval of time, we'll say t2, we'll notice that this one has dropped even more because it's accelerating downward. This one has also dropped more, but still moving to the right. And lastly, pretty close to right before they land. Okay, so this is kind of like snapshot at 4 different moments in time. So these would be 2 different motion diagrams. And the important thing here is that this demonstrates to us that an object's motion in each dimension is totally independent. So motion in the horizontal dimension does not affect motion in the vertical dimension, and vice versa. Which is why that this one moving straight up and down, and the vertical part of this projectile's motion, which would be up and down, are actually identical. But let's go through that in a little bit more detail. Let's start by looking at what they share in common, which is the vertical motion. Now, initially, what we need to remember is that gravity is only applied in the vertical dimension. So the acceleration due to gravity only affects the vertical part of the motion. So initially, both of these have an initial velocity of 0 in the y dimension. So you'll notice what I've done here is I've put v y naught equals 0. So that's v with a little y and a little 0 equals 0 for both of these projectiles. Now, why have I put the y there? Well, now that we're moving in 2 dimensions, we need to start separating what is in the vertical dimension, which we typically label as y, and what is in the horizontal dimension, which we typically label as x. So for both of these projectiles, vertically speaking, they are at rest initially. Yes, this one is moving horizontally at that moment, but remember, because it's a horizontal projectile, none of that motion starts in the vertical. So the vertical velocity, initial velocity for both of these projectiles is 0, and we know that the acceleration in the vertical dimension for both of them will be 10 meters per second squared down, because that's the acceleration due to gravity. So let's look at the next instant. Well, both of them have gained a little velocity in the y dimension. Well, as time goes on, they're going to accelerate even more vertically, and they're going to gain even more velocity in the y dimension. Now let's start to look at the horizontal, though. So the important thing here, though, is that gravity, since it's not affecting the horizontal motion of either projectile, well, then there's going to be no acceleration in the horizontal direction. There's nothing to provide that horizontal acceleration. Now, I want to be careful. Some people might be looking at this and going, well, wait a second, how did it gain this initial velocity? But remember, for any sort of projectile motion, including free fall, we only look at the instant it leaves, whatever it's launching it or is throwing it. So in this case, the instant it leaves the cannon to the instant right before it hits the ground. So it already has gained that initial velocity before we start examining it. So there's no horizontal acceleration here, and that tells me that the initial velocity in the horizontal dimension we'll label as Vx naught. There is no acceleration in the x dimension, and we'll say for the dropped projectile, its horizontal velocity would be 0 because it's not moving side to side. And if its horizontal velocity, initial velocity is 0, and its acceleration is 0, then this will never move side to side, which makes sense. But if we look at the horizontally launched projectile, we'll notice that because there's no acceleration, the initial velocity in the x is really the final velocity in the x, and the only velocity in the x, because no change in the horizontal velocity is occurring. So for every projectile motion here, every piece of it, we see that it has the exact same horizontal velocity. So now I have, and it's important to notice this, some vectors going on. And what we notice is that we have, in this one, the dropped one, we only have vertical vectors, but in the horizontal one, we start with only horizontal, but we gain a vertical to have both horizontal and vertical components of its total velocity vectors, which will look like so. But if we were to add these components tail to tip, so if I was to move this one over here and move this one down, we would see that it would go right there. here it would go right there. Here it goes. And you notice it's all in line with the trajectory. The velocity, the total velocity vector, follows the trajectory. But it's composed of horizontal components that do not change and vertical components that start at 0 and steadily grow in size. So now that we've examined the situation more conceptually, it's important to start discussing how can we solve these types of problems. So let's say a cannonball is launched horizontally from a 42-meter high cliff with an initial velocity of 100 meters per second. Notice horizontal. What is its range? Well, first off, what do we mean by range? Range just tells me how far, so we're really asking for the horizontal displacement. So we'll notice here that we're looking for this range. We know it's a 42-meter high cliff. We know the initial velocity is 100 meters per second, so we have some givens here, and we probably know that g is involved somewhere, 10 meters per second squared down. But it starts to become an issue because we're like, well, I have an initial velocity and a displacement and an acceleration, but these dimensions are different. Where do I even start? Well, for any kinematics problem, and this is ultimately a two-dimensional kinematics problem in a specific situation, remember we always want to start off by identifying our givens, what we know, and our unknowns, what we want to find out. So to start doing that, what I want you to do is I want you to think about the cannon we were just looking at, and I want you to rotate your perspective. Imagine that you're looking at the cannon head-on. So imagine you're really far away from it, you're looking at it head-on. And what we notice is that if we're looking at it head-on, we don't see any of its horizontal motion. We only see the vertical part of its trajectory because it would be coming at you. And what you might notice is that this looks a lot like a situation we've already encountered because this looks a lot and is basically identical to dropping. So let's start identifying our givens here. And we have a few. First off, we know for sure that the delta y, the displacement in the y dimension, is 45 meters. I guess I should say technically down because we start here and it's going 42 meters down. We know already, so let's think about dropping situations. We know that the acceleration in the y dimension is g, which is 10 meters per second squared down. And what else do we know from things that are dropping? We know that their initial velocity, but notice I have to put the y here, the initial velocity in the y dimension, is 0. So, okay, notice I put y's on each of these. That way we can keep the vertical separate from the horizontal. But what are our unknowns? Well, we don't know time, and we don't know the final velocity and the vertical. So now we're actually going to rotate our perspective again. So look back at the initial cannonball situation, and we're actually going to rotate it so that we look at it from overhead. So from an overhead perspective. And what we'll notice is because we're only looking at it from the top, we can't see any of the vertical. Now we can only see the horizontal part of the trajectory. And what we notice is since we can't see the vertical part, and we said, remember, it's not accelerating in the horizontal, this is actually identical to a constant velocity situation. Let's start talking about our givens once again, our unknowns. Well, for the givens, we know for a fact that the initial velocity is actually the same as the final velocity in the horizontal, which is 100 meters per second. If I want to be real specific, I can say right. And that the acceleration in the horizontal is 0. We just know that already because there's nothing affecting it in the horizontal dimension. Our unknowns will once again be time and delta x, the horizontal displacement. So now looking back at this problem that we were looking at a minute ago, let's start to really identify all the givens and unknowns we've already talked about, specifically keeping them separate into a vertical column and a horizontal column. Okay, well, what are we looking for? We want delta x. And if you look at your kinematic equations, I can't use any of the kinematic equations I know without time because of the fact that the acceleration is 0. How can I get this time? Remember, the time, though, is going to be the same in both. however much time it takes to fall vertically is the same amount of time it's going to take to go horizontally. So this time is going to be the same in both dimensions. And if that is the case, we can solve for the time in one dimension and then use time in the second dimension. So I've gone ahead and written the givens and unknowns again for the vertical and horizontal. Notice I'm keeping them in two separate columns. I want them to be completely separate. I can't go anywhere between the two except for what we're going to do in a second. And I want to find time in the vertical dimension so that I could figure out time in the horizontal and use that to solve for delta x. So I have delta y, vy naught, ay, and t. And to solve for time, I'm actually going to want this equation. Notice I put in a y and a y. We need to do that to make sure we're safe. Okay, so luckily for us, we are looking for what? The time. Because vy naught is 0, I'm going to go ahead and say that this whole first part becomes 0. And therefore bring my equation down a little bit so we can say, well, we're actually solving for this equation. So now that I have this, how can I simplify this a little bit? Well, I'm looking for t, so I'm going to multiply by 2, divide by ay. Now that would be squared, so I need to take the square root. And lastly, we plug in some numbers, and we get, if you plug in your calculator, don't try to do this in your head, you should get 2.9 seconds, roughly speaking. Okay, I know for a fact that 2.9 seconds is the same amount of time here. So I've actually given myself a new given. T is equal to 2.9 seconds. So now I want to solve a new kinematic equation in the horizontal dimension that allows me to find delta x. Well, let's go ahead and stick with this equation here. Delta x equals vx naught t plus 1/2 axt squared. And if we first start by solving, the first thing I want you to notice is that ax is 0, so this whole second term goes to 0, and I'm left with delta x equals vx naught t. That's what I want, so this is pretty much solved. So now I need to substitute in, which would be 100 times 2.9 is 290, and congratulations, we just found the range of this projectile, 290 meters. So that was a typical strategy for solving horizontal projectile problems, and we want to go through these steps every single time we do one of these. The first thing you need to do, just like any kinematics problem, you need to identify the givens and the unknowns. But specifically, we want to make two different columns. One for our horizontal givens and unknowns, one for our vertical givens and unknowns. And we do not want them to cross, except for the fact that we're going to ultimately solve for time in one dimension, because time is the one factor that can cross between the two. So we use the guess method in either horizontal or vertical to find time, and then from there, we're going to use that time in the other dimension, and then use the guess method to find whatever the wanted unknown is, the range, the height, the velocity, whatever. Now, a lot of times, I'm not going to say every time, a lot of times you're going to use this particular equation, same one in the vertical and horizontal dimensions. But what I want to recognize is when we have these, I always recommend writing them out first to make sure you don't make a mistake. But in the vertical dimension, if it's a horizontal projectile, there is no initial vertical velocity, so usually this first piece will cancel, and in the horizontal dimension, there is no acceleration in the horizontal, so this piece will cancel, and that greatly simplifies our equations. So what are the main takeaways for this video on horizontal projectiles? Well, one, can we compare and contrast a dropped projectile from a projectile launched horizontally? Can we utilize the independence of motion of an object in each dimension? AKA, if it moves horizontally or vertically, either one does not affect the other. Can we describe the horizontal and vertical motion of a projectile launched horizontally? Can we describe all of the factors vertically and all of the factors horizontally, both qualitatively and quantitatively? And can we employ a strategy to solve horizontal projectile problems? Basically saying, 1, identify your givens and unknowns in each dimension. 2, solve for time in one dimension, usually the dimension that what you're looking for is not in, and then take that time, put it in the other dimension, and solve for what you want.